Hello students, topic torque on a current loop for NEET and JEE. First we will do a quick review about the theory. Current carrying loop acts as a magnetic dipole. That means when the current flows, one side of a loop acts as a one pole and the other side is act like a opposite pole. I am taking an example of a current carrying circular loop. Okay, so in the circular loop, the current is going in this direction. Okay, I apply the right hand rule on the top side. So I got that the magnetic field is going away. Okay, that means this side is act like a north pole. Okay, I apply the right hand rule in the bottom side. So I am getting that the magnetic field is going into it. So this side of the loop is act like a south pole. That means you see that when the current flows, one side of the loop is act like a one pole and the other side is opposite pole. Here the top side is act like a north pole and the bottom side is south pole. Okay, so two poles are separated by a small distance. So this is act like a magnetic dipole. Similar way, all the current carrying loop act as a magnetic dipole and it possesses a magnetic dipole moment, that is M is equal to NIA. What is this N? N is the number of turns, I is the current through the coil and A is the area of cross section. This magnetic dipole moment, is a vector quantity. Its direction is similar to the direction of the area vector. The direction of the area vector can be found out by right hand rule. Okay, so now you see this is a current loop, is a circular current loop. The current is in this direction, so I am going to apply the right hand rule. Curl the palm in the direction of current, then the thumb gives the magnetic dipole moment direction. So here the magnetic dipole moment direction is upwards. Okay, if the current is in opposite direction like this, the palm curled in this direction, thumb is to be in the downward direction. So the magnetic dipole moment is downwards. Okay, this is the way we can find out the direction of the magnetic dipole moment. Okay, then a current carrying loop is placed in a magnetic field will experience a torque. Okay, I am taking an example. A rectangular loop is placed between the magnetic field. This is a two magnet, north pole and this is the south. There is a rectangular loop. This is a rectangular loop is placed between this. Okay, the current is going in this direction. The current is in this direction. So the magnetic dipole moment direction is found out by right hand rule. So if you curl the palm in this direction, current is into it. So here the magnetic moment direction is like this and the magnetic field direction. Okay, so the magnetic field direction is like this. This will be. Okay, so now you see that the magnetic field and magnetic moment is making an angle theta. Okay, so this rectangular loop is experiencing a torque. The net force is zero. Net force is zero. The two forces are acting along the opposite direction and it is equal amount. These two forces are acting in the loop. These two forces are in the opposite direction and we have different line of action. You see this force or this line of action and this force or this line of action. So that this rectangular loop experience a torque, that is the torque is equal to mp sin theta. Okay, and torque is, we can write in the vector form m cross b, and the direction of the torque is perpendicular to the plane containing m and b. Okay, this is the torque acting on a rectangular loop is placed in a uniform magnetic field. Similar way, any closed loop is placed in a uniform magnetic field. If it carries a current, it will experience a torque. Okay, that formula is m cross b. Okay, now we will discuss the special cases. Case 1. Okay, case 1, theta is equal to 0 degree or theta is equal to 180 degree. Okay, so what about the torque? Torque is equal to mb sine 0 degree. Okay, now what about sine 0? Sine 0 is 0, so the torque is 0. If it is 180 degree, sine 180 also 0. Clear? Okay, then now we see. Then the case 2. Case 2, theta is equal to 90 degree. That means the angle between the magnetic moment and the magnetic field is making an angle 90 degree. Okay, that means you can see that the plane of the loop is along the direction of the magnetic field. Plane of the loop is along the direction of magnetic field. The torque is mp sine 90. Sine 90 value is 1. So the torque is mp. The torque is mp. This is the maximum torque acting on the rectangular loop. Okay, the torque is maximum, theta is equal to 90 degree. Okay, this is about the theory. Now we go to the problem. First we see the type 1 problem. A coil placed vertical plane and is free to rotate in a magnetic field exists such that the magnetic moment and B are in the same direction. What is the angular speed acquired by the coil when it has rotated 90 degree? Okay, clear? So they are given that there is a coil is there. That coil initially making an angle theta with the magnetic field. That means the magnetic moment of the coil and B is 0 degree. After that the angle is 90 degree. Okay, it has to be rotated with an angle of how much? Rotated with an angle of 90 degree. Okay, then so we need to find out how much is the angular speed acquired by this. Okay, now we will see. This is the north and this is the south. Okay, the magnetic dipole moment is in this direction and the magnetic field also in the same direction. Okay, so theta initially is 0 degree, then theta f is how much? That is 90, that is pi by 2. Okay, when a current carrying loop is placed in a magnetic field, will experience a torque. The torque formula is mp sine theta. Okay, and the torque based on the moment of inertia, we can write it as I alpha. Okay, these two equations, from that we can write it as I alpha is equal to mp sine theta. What about alpha? Angular acceleration, that is equal to d omega by dt, that is angular frequency. Okay, then mb sine theta. Okay, this I can write like this: d omega by d theta into d theta divided by dt is equal to mb sine theta. Okay, what about this? This is the angular frequency, that is omega into d omega by d theta is equal to mp sine theta. Okay, this I will come this side become division and d theta goes to this side become multiplication. So I'll get it as omega d omega. Omega d omega is equal to, that is here I can write. Okay, so omega d omega is equal to mpi by sin theta d theta. Okay, now I can integrate this side and this side. This is from 0 to omega f. Okay, this is the angular frequency. Okay, what about the angle change? Initially 0 and the finally is pi by 2 angle. Okay, now we can see this. This is how much you will get? Omega square by 2. Okay, this is 0 to omega f, and mb by I is a constant. Integration of sin theta is minus cos theta. Lower limit is 0, upper limit is pi by 2. Okay, then now you see this. Substitute the limit. So here you will get it as omega f square by 2 is equal to mb by I. If you apply cos pi by 2, that is 0, then next cos 0 is 1, so you will get that cos 0 you get. Okay, cos 0 is to be 1, then now you will get this omega f square is equal to mb divided by I. Then omega f is equal to square root of 2mb divided by I. This is the angular frequency or angular speed acquired by the rectangular loop or a coil. Okay, this is about the type 1. Now we will see type 2. A coil in the shape of a equilateral triangle of side L is suspended between the pole piece of a permanent magnet such that B is in the plane of the coil. If due to current I in the triangle a toe acting on it, then the side L of the triangle is. Okay, so what they are given? They are given that a equilateral triangle loop is placed between the poles of a magnet. It experiences a torque. Then what is the length? Okay, so you see here, this is the poles of the magnet, north pole and the south pole, and place an equilateral triangle in such a way that the magnetic field is in the plane of the loop. Okay, the current is going in this direction. Okay, then what about the magnetic field direction? Like this. Okay, then what about magnetic dipole moment direction? Because there is a torque acting on it, we need to find out the torque. For that we have to use the magnetic dipole moment. Magnetic dipole moment is m is equal to I into A. Okay, I into A. Here the A is the area of the equilateral triangle. So that is root 3 by 4 L square. Okay, then the direction of M is similar to the area vector direction. So curl the palm in the direction of current, then the thumb gives the direction of the magnetic dipole moment. So the magnetic dipole moment direction is going into it. Okay, so the torque is mp sin 90 will get, actually sin theta, this is sin 90, so we will get it as mp, and m value already we find out, that is I into root 3 by 4 L square into B. Okay, we need to find out L, so L square we'll keep it here, remaining we'll take it to this side. So 4 into tau divided by root 3 ID we will get. Okay, then what about L? L is equal to square root of this thing. Okay, that is 4 tau divided by root 3 IB. Okay, in that this square root of 4 is 2. So 2 into square root of tau divided by root 3 IB. Okay, this is the length. Okay, this is about the type 2. Now we will see type 3. Rectangular coil of 100 turns is placed in a uniform magnetic field 0.02 divided by root 2 J Tesla shown in the figure. The torque acting on the loop is, they given that a rectangular loop is placed in a uniform magnetic field. What is the torque acting on it? Okay, the torque acting on a rectangular loop is M cross B. What is M? M is a magnetic dipole moment, that is equal to NIE. Its direction is equal to the direction of the area vector. How we can find out the area vector direction? Curl the palm in the direction of current, then the thumb gives the magnetic dipole moment direction. So here the magnetic dipole moment is coming out. Okay, that is the direction of I. Okay. What about the number of turns? That is 100, and the current is 0.02. This I can write it as 2 into 10 power minus 2. This is a rectangular loop, so area is equal to L into B. That is this side into this side. This side is how much? That is 4 into 10 power minus 2 into, what you will get this side? That is 8 into 10 power minus 2. 4 into 8, that is 32. 32 into 2, that is 64. You are getting? This is 10 power 2 plus 2, and this is 10 power minus 2, cancel. Then remaining 10 power minus 4, and that is direction is how much? That is the direction is I, and the unit is meter square. Okay, sorry, unit is ampere meter square. Okay, then this is the magnetic dipole moment. Now we can find out the torque. Torque is equal to 64 into 10 power minus 4 I cross B value. What about the B value? That is 0.02 root 2 J. Okay. So now this and this we can cancel. That is, before that we can do like this. 64 into 10 power minus 4 into this I can write it as 2 into 10 power minus 2 divided by root 2. Okay, then I cross J. What about I cross J? I cross J, we can write like this. This is I, and this is J, and this is K. So I cross J, what you get? That is K. Okay, so this how much you are getting? You are getting 64 root 2 into 10 power minus 6 K. Okay, this is the torque, and its unit is Newton meter. Okay, this is the torque acting on this rectangular loop, and that is about the type 3.
Thank you for watching the video. Please subscribe my channel. If you like this video, please put like.